So in the last class, I forgot to mention one remark. Just a remark. Of course, if you have already done compactness, you should know this, but I'm supposed to record this. It is just if X is compact, X is a compact metric space, and Y is another metric space. Of course, Y you have another Y. And if you have F X to Y, a continuous bijection. Okay, before that, we make a definition. If you have a F from X to Y, which is continuous, a continuous bijection such that F inverse is also continuous, is called a homeomorphism. Okay. Okay. If you have two metric spaces, X and Y, there is a continuous bijection such that the inverse is also continuous. Sometime it may be a bijection, but the inverse may not be continuous. So inverse is also continuous. Then we say that it is a, I mean, for example, if you have the same space X and Y, but with different topologies, with give rise to different topologies, then the inverse need not be continuous. If that is a bigger, I mean, you can arrange it that way. Okay. So it's a continuous bijection such that F inverse need not, sometimes F inverse need not be continuous. So F inverse is also continuous. So that is what is called a homeomorphism. Homeomorphism is a topology, that means we identify X and Y topologically. They have the same open sets, and the open sets can be taken from here to here by F and here to here by F inverse. That's what it means by homeomorphism. For a metric space to be identified, we need isometry. The metric should be preserved, which we have already defined. D of xy is equal to D of f of x, f of y. Distance between x and y is same as f of x and f of y. That is what is called isometry. If there is an isometry which is an onto, isometry is always 1, 1. If it is onto, you can check it. Okay, if it is onto, then we say we identify those two metric space. But here, if we are identifying these two metric spaces as topological spaces. Okay, that's what it means by a homeomorphism. Continuous bijection such that so you don't need this condition when X is compact. That's what this says. Okay, that's big. F is continuous bijection, then F is a homeomorphism. Okay. So proof is easy. I will tell you orally. It is just that if it is continuous, it takes inverse image of open sets to open set. But when it is compact, X is compact, any closed subset is also compact. It will take compact subsets to compact sets. So it will take closed sets to closed sets. But then, I mean, in general also, even if it is not onto, you can check that it is actually open map. You need a little bit. But here it is clear. It is just the complement. F of A complement is F of A complement. Here you can check, which is not usually true, but still you can check the openness. It's an exercise. But here it will take compact sets to compact sets, so it will take to closed set to closed set, so open set to open set. So since it take open sets to open set, it has to, F inverse will bring open sets to open sets. So F inverse is also continuous. F inverse is continuous. If F inverse bring open sets from X to, F inverse is from Y to X, it brings open sets to open sets here. But since F takes open sets to open sets, is 1, 1 on its bijection, F inverse will also take, so it's continuous. F inverse will also take open sets to open sets, so it's continuous. That's what homeomorphism. So this is this I should have recorded last class. So so this is fine. We'll move on to, I mean, what will happen? What do you think? Huh? Yeah. Do you think so? Does it have to be so? So we were discussing Arzela-Ascali theorem in the last class. Okay. So which says, if this is the theorem, we had Arzela-Ascali theorem. We have C of x, where x is a compact metric space. Then you have a subset contained in this. Okay, this is compact. This is what we proved, which is equivalent to saying this is closed, uniformly bounded. I mean, it's bounded in this as as a subset of this metric space. Okay, so which is equivalent to saying it's as functions they are uniformly bounded. There is a single bound for all the functions here. Okay, so that is uniformly bounded, and further there is one more condition. It is equicontinuous. Okay, equicontinuous is just a generalization of uniform continuous for a collection of function. There should, given epsilon, there should exist a single delta for all function for all xy, such that the continuity condition is satisfied. Okay. Okay. So example, so we have already seen examples of uniform, sorry, equicontinuous function. Here we want to see another new example. So we take C of x. Okay. So let us take x, y compact, two subsets which are compact subsets, compact metric spaces. And we have a single function k from x cross y. This is cross, this is x. X cross y to C continuous. We have a single function continuous. Okay. Earlier we had a single function on two variable, and then we fixed one variable and considered the collection of, fixed one variable and considered a collection of functions through that variable. That is uniformly contact. But here we will do something else. We define the following. We define Tk. T is an operator corresponding to this k from C of x to C of x. Defined by define Tk by. So to define Tk is a function from C of x to C of x. So if you have a take a f here, you apply Tk, that should be a function here. So you have to say what is it at x. That's what you have to say. So Tk acting on a function at x. Maybe I'll write it there. There is not, I thought I will. This is the definition. Tk f acting on x is equal to integral over x. Okay. I generally wrote it x cross y, but you need much more than measure theory or something. So I take it as, I want to use only Riemann integrable. So I take this as C01. Okay. This is not needed. I'm sorry. You can take xy and take x equal to y equal to 0, 1. Otherwise, we need to make it complicated. Okay. So C of k is any function. Okay, let me repeat. We don't have any metric space. You can define through metric space also, but then I have to define the integration. Okay, integration on compaction with respect to what measure and all that. Okay, so that's why I just want to take just Riemann integration is fine. Okay, any continuous function is Riemann integrable, so I can work with that. Okay, so that is why. So I start once again from 0. We have a function from 0, 1 cross 0, 1 to C, a single function k, which is continuous in two variables. Okay. Then corresponding to that, Tk I define from C01 to C01 by the following. So to define Tk, that should be another function. So Tk at this is between 0 to 1. F k, I put the k xy, f of y dy. Okay. Otherwise, you have to use measures and other things. Okay, dy. That's all. You just integrate it. You have kxy, which is a function in two variable. You integrate with respect to y variable, so it's not there. It depends only on x, so it is this. What? Which f is any function for all fn. Okay. F is a function, so this f of y is well defined. So tkf, I have to define what it is, so it should be a function here. Okay, tk is say it again after 1, 1. There is no definition of k. K is anything, any function below which C by by. Define this by. I wanted more space, so I wanted right here, so I wrote the by on the top. Any function. For any k, I defined this. There is a case, tk is defined. Define k.
tk operates on f, right?
tk operates on C01, yes. tk, k is any function. Given any function, I define an operator. It's a call operator, or you call it a function. Okay, given a function k, I define a function. This is a linear function, so it's called operator. Okay, it's also called if that is a vector space, if you have a linear space, you call it linear operator. Okay, I mean it's also a function. Okay, so it's a linear function. Linear means linear function in vector space. It's the same thing. Okay, it's a linear function, so it's also called operator. So tk is defined from C01 to C01. When k is there, I define a tk such that tkf I integrate. I just write this and integrate with respect to the second variable. Okay, since k is continuous, if you take xn going to x, okay, then k is continuous. So kxn y will go to kxy. Okay, and it's all nicely bounded. You can apply LDCT and take the limit inside. Okay, k is bounded by some m, and that with respect to that m, it's integrable. Okay, if you have some functions fn, all are less than some single function g, such that integral mod g is finite, then you can take the limit inside. We have already used this several times in the probability course, and we have used here also for limits and other things. You can take but there is no uniform. I'm just for each xn I want to take it. No, I mean you can consider uniform convergence also if you want. I mean, if you fix as a function of, if you fix this, then I mean you can consider as uniform function also. But here I just want to take the variable xn inside. This is fine. Okay.
C01 cross 0.
No. tk of f
is belonging to C01 and x is belonging to 0. It's basically tk of f comma x, right?
tk of f is a function. tk is a map from C01 to C01. Okay, tk takes a function here to function here. So tkf is I am defining, which is a function here. That function evaluated at x is this. Okay, f is in C01. tkf should be in C01. Okay, so to say a function is in C01, define a function in C01, I have to define tkf at x is this. Okay, so I am verifying that it is continuous. Since this is continuous, xn going to x, kxn will go to this, and you can take the limit inside. That's the argument I gave here, which we have gone through several times. You just check it, because this is a nice function. This is a continuous function. This will be bounded by some number m, and that integral m is with respect constant. You can integrate it, so you can take the limit inside. There may be other arguments. Okay, so you can integrate it. You can take the limit inside. So this is continuous. If xn goes to x, tk of xn will go to tk of x. This is continuous. So okay, so tkf belongs to C01. That is, it is continuous. I mean, I have already said everything, but still you verify, convince yourself. It's an exercise, easy exercise. Okay, so tkf is a continuous function. Now you can consider this collection, that is equal to tk of f. Okay, where all those tkf such that f is in C01, of course, f is in C01, norm of f infinity is less than or equal to 1. You take it and take the closure. I take all functions such that its norm is less than 1, supremum norm of f is less than 1, less than or equal to 1. Then I take the closure. That may not be closed. K is fixed for the whole thing. K is fixed. F is varying. F is in C01. Okay, and f is varying. So this is a collection of functions. For each f, there is a tkf. You take all the tkf, and this closure is taken again in C01. Okay. you take f, vary f, TKF. You are not taking all f, you are taking f less than or equal to 1. I mean, norm f infinity less than or equal to 1. Then you take the closure in C01. This is the closure with respect to C01 norm. Okay. So if you want, you can write it this. The closure is there in that. Yeah. Exactly, precisely. That's why we are. This is an example for Russell-Ascari theorem. Okay. We are going to apply that. That's why. Huh? Of course, not countable. No countability. It's for anything. Okay. So we have to verify. So this set F is closed. Okay. Russell-Ascari, there are three conditions. The subset has to be closed, and the subset has to be bounded, and the next thing is it has to be equicontinuous. So we close this clear. We are taking the closure, so it's closed. So we have to talk about. We have to verify it's bounded. Okay. Each f is continuous. We have to use this condition. You have to write it. It's not very clear. So what we have to prove? We have to talk about TKF. TKF, where f coming from this. I mean, this set is bounded is enough. Closure will also be bounded. Okay. So that's fine. Closure will not. Okay. So we have to verify this. We have to find a uniform bound for this. Okay. So TKF of x, which is equal to integral whatever, integral 0 to 1 kxy. K is a single function, f of y dy. Okay. We want to take the mod of this. We want to take the mod of this. That is less than or equal to integral 0 to 1. K is so that is in x and y. So you can take the supremum of f. You can take the mod inside, of course. Okay. Which is less than or equal to mod inside. Okay. Inside mod. Now this you can take the supremum of this. The whole integral will be less than this. This is positive, that is positive. The whole integral will be less than this. So you can take norm f infinity, and you can also take k infinity also. Norm k infinity in x cross x. Okay. That also you can do. Then integral there will be only one. So this is less than this. Okay. For all x. Right. You can take the supremum of this with y if you want. That you can take, but you can take the supremum of that. Kxy is less than k infinity. K infinity is the supremum norm in x cross y. I mean 0, 1 cross 0, 1. Okay. You can take the supremum of that. You can take the supremum of this. This whole thing is less than that number. So the integral will be less than that number. So you can do this. Okay.
All by the set of f, and then supremum of all x and y.
Yes.
0, 1
Yeah.
of
Wherever, how is supremum norm is defined? Any set you can take. Okay. You f by 1. What?
f norm of f at 1.
That's right. Sure. I'm just writing it. Yeah. I mean, I wrote it for a reason. To actually, you can show, if you write it like this, you can show that tk is a continuous function. It is not clear to you, no? So I wrote it for a reason. Yeah, I mean, I didn't think about it, but that is why it's being written. Okay. Yeah. So see, you can see that this implies that this is a linear function, right? TKF minus g, TKF minus TKG. This whole thing, same thing implied. This because it's linear. You can see that it's linear because it's integral and it's linear. So which is equal to TKF minus g. Okay. This is norm infinity, which is less than or equal to this whatever f infinity, norm k infinity. Sorry, here it is f minus g infinity. Okay. So TKF minus TKG is less than f minus g k infinity, some constant. This one. How is this equal to this? Just write down. It is just TKF. You have a f here. If you have f minus g, you can write integral, everything is linear. Multiplying by a function is linear.
For the last expression,
The same thing I'm using. This is true for any f. Okay, this is true for, I mean, okay, oh, no, wait, one more step. Then I write, sorry. This is true for all x. Okay, here there is no x. Okay, now you take the supremum over x. Okay, so this implies norm of TKF infinity is less than or equal to norm f infinity times norm of k infinity. Okay, I mean, clearly the definition is written. If you have any confusion, you verify this thing. So this implies norm of TKF minus TKG, okay, infinity is equal to norm of TK of F minus G, that is linear, which is less than or equal to by the same thing, norm of F minus G infinity, norm of K infinity. Okay, this is not, this implies TK is continuous, okay? Uniformly continuous, in fact. What supremum? Which supremum? Doesn't it? Huh? Does it not exist?
I mean, you'll have to, for that, you're assuming that it is continuous, right?
Of course, we are assuming continuous. What is continuous? No. TK, where are we taking supremum of TK infinity? TKF. TKF is less than this, so TKF is less than this. Where are we assuming? This is less than this for all x. You take the supremum, so the supremum is less than that. That's what supreme. Huh? Right. Which one? This one. Here. You take the supremum of this. Okay. In xy, x this. This whole thing is less than that supremum, this number. Integral, that is 1. Integral of 1 is 1. If you want, you write it as 1, 0 to infinity dy. Okay. 1. That is just 1, right?
We haven't used the fact that KKF is the element of
TKF is a?
we haven't used the.
We will prove it in this condition.
Here it is.
This is just, I'm showing you an extra thing. This is not part of it. TK is actually a continuous function. TK itself is a continuous function. Okay.
Take the fact that.
No, I'm coming to that. Okay.
Period to apply.
No, it's not neither. It's extra. I'm just because I mean this is just to show that continuous functions, this kind of continuous function exists. Supremum of what? Of course we are using. Yeah. It is continuous, so it will exist, right? It is there. C01 to C01 as a function between these two metric space, complete metric spaces, it's continuous. Okay. Yes. It's good having a lot of questions like this, and it's nice to go like that. Okay, I don't mind. But of course, I have finite energy. If I have to repeat again and again, that will be a problem. Once I have said, you should notice that I have said. Okay. Yeah. Okay, that's fine. So we have this condition. So we have, anyway, I'm writing it again. TKF infinity, this is a norm. This is a function. This is a function, and its norm is less than or equal to norm f infinity times norm k infinity. Okay. So when if is less than or equal to 1, this implies TKF is bounded by k infinity, right? So there is no f there. So this implies that set f is uniformly bounded. Uniformly bounded means it is bounded in C01. Okay, that's what it means. As a subset of the metric space C01, it is bounded. By that we mean it is uniformly bounded. Okay. F is bounded. So F is closed, F is bounded. EQ continuity is the only thing we have to verify. Okay. So that's also easy. You can see. So to verify EQ continuity, what we have to do for any TKF, which is the function we want to consider. We want to say that this, when f varies in that set, okay, when varies f infinity less than or for all function f infinity, you should find a uniform delta given an epsilon greater than 0. Okay, so given epsilon greater than 0, we have to get a uniform delta for all f, for TKF for all f coming from this. I mean, given a epsilon, you will not be able to find a delta for all f, but for all TKF, you will be able to find. Okay, that's what we are going to do. Okay, TKFX minus TKF, oh, there is x prime, okay, because y will be there in the integral, so I use x prime, okay. Let me just write this, okay, that is less equal to 0, 1, that is equal to, okay, let's take it inside mod, it's equal to k of xy minus k of x prime y, okay, f of y. So, I mean, f infinity you can take, okay, if you want. This is less than or equal to norm f infinity, which is less than or equal to 1. Okay, this is okay. Yeah, k is continuous. You are going to. Is this okay? Same thing I have already done. TKF, TKX prime. You will only have this. Then there will be a f there. F of y will be there. I just swallowed it because it's less than 1. Okay, norm is less than 1, so it's okay. Okay. So this is this. Now you just have to, this integral is between 0 to 1 with respect to then. So if it is less than any epsilon, the integral will also be less than epsilon only, because epsilon integrated, constant integrated. Now you can choose. Now it doesn't depend on that. K is a single function. Okay, so there exists, if, I mean, this is true, no, if x minus, this is 0, 1, x minus x prime less than delta, y minus y prime, there exists single delta. Okay, there exists delta greater than 0, such that if this is there, then k of xy minus k of x prime y prime is less than epsilon. K is, yeah, k is uniformly continuous. K is continuous on a compact set, uniformly continuous. So there exists a single delta for all these things. Okay, now you can take y equal to y is same, y equal to y prime, which will still be less than delta. So this is true. So this implies if x minus x prime, I mean, you can take less than delta, y, you can, I mean, for r y this is true. You can just, I mean, this is for y and y prime varies within delta, this is true. You can take y equal to y prime, then it will be still less than delta. So this is okay. Okay. So then that implies TKF of x minus TKF of x prime is less than or equal to whatever, 0 to 1, that this is less than this, epsilon times Ty equal to epsilon. That's all. TKF of x minus TKF of x. That is equal to, by the definition, whatever we have, which is just ky times f of y, kxy, kx prime y, then in the other one you get a f there. That f is, you can have a mod f because it's an inequality. Okay, and the mod f is less than or equal to 1, so it will be swallowed. Okay.
Is there exist a k? Is that dk is 1
TK, yeah, it's possible. TK, no, it will not be a homeomorphism. TKF,
dk, not dkf. dk. Like for every function there is a unique.
That one has to work it out. Usually, I mean, from operator theory, I know that TKF need not be even closed. This is closed. It need, this norm f infinity less than or equal to 1 is closed, but TKF need not be this thing. That's why I take the closure. It need not be closed. So I mean, yeah, it may not. So we have done. So it's equicontinuous. This is the definition of equicontinuous, and we are done. So even though this collection, all f such that this is not compact, This is closed and bounded, this set. All f such that norm f infinity less than or equal to 1. This set in C01 is not compact. Okay, which is closed and bounded, but infinite dimension, that's not compact. We have shown that t power n is something which is there, which has a finite distance, so it's not compact. But if you apply this function and then take the image, that is compact. Okay. This operator is what is called a compact operator. It takes bounded sets to compact sets. Okay, so it's a compact operator in functional. Exactly, exactly. In vector spaces, bounded sets are non-linear space. Vector space, the bounded sets are just dilation of that, which is a continuous one. Okay, so you can see that R times that. So you can take any ball centered around somewhere. So that will also work. Okay. Okay, that's all for Arzelà-Ascoli theorem. We'll move to something new. If you have any doubt, you can ask me. I'll just write here itself. What is the next? We want to discuss. So from here onwards, we will discuss something about more about the consequences of completeness. Okay? Baire's theorem and all that. Okay? So before that, we will discuss what is called contraction theorem, fixed point theorem, contraction theorem, Banach contraction theorem. You have seen it in your class? Huh? Okay. Should I do that?
Yes.
Huh? Okay. Okay, I will then do some few versions of it. You have seen only one version, right? One version. What is the second one?
Other is that the C we take, if you put that equal to 1, then the original space needs to be compact and then again that.
So if it is X is compact, you don't need C. You don't, I mean, it's just less than sign. Okay. So that proof we have seen. Exercise. I've seen it as exercise. So, okay, we will go through 3-4 things. 3-4 contraction theorem. Okay. 3 contraction at least I have in mind. Okay. So one is, what is a contraction? Metric space T from X to X itself. It has to be X to X itself. Is a contraction. If there exists a C strictly less than 1, strictly greater than 0, such that d of Tx, Ty is less than or equal to C times d of X and Y. That's all. Okay. Notice T is continuous. Okay. This is less than this. If you give an epsilon, if this is less than epsilon by C or something, then you get the delta to be epsilon by C and you will work. Okay. Or you can check the convergence. Xn converges to something, Xn converges to some X here, then Txn will go because of that. Okay. So it's clear. So continuity is clear. It's uniform continuity, it's Lipschitz continuity, whatever. The theorem is the following. This is contraction, Banach contraction theorem. So T is a contraction. Then there exists a fixed point. X is complete. Good. X is complete. I mean, anyway, when I prove it, I will get it. Okay. And it's good that then we will remember that completeness is needed. But I have done it several times. I don't remember to state it. Only while proving, I remember. Okay. T is a contraction. Then there exists a fixed for T. That is, there exists X in X such that Tx equal to X. Okay. Okay. Proof. Of course, we have to take some Cauchy sequence and we have to use the completeness. From here onwards, in next 3-4 classes, completeness will be there all the time. Even if I don't forget to mention, you should remind me, or okay, we will assume completeness. Okay, we are going to see the consequence of completeness. Okay, okay. So we have to get a Cauchy sequence somehow. So choose any start with any x naught in x, okay, then x1 equal to tx, xn equal to t xn minus 1, okay, like this. Okay, well, you iteratively define. So we want to show that this converges to something, and that is a fixed point. Okay, that's what we want to show. Here there exists a unique fixed point. There exists a there exists a unique fixed point. Okay, I've changed it. Choose any x naught, then this. Okay. To show that this converges, we have to show its quotient. Okay. So to show quotient, we consider this. Okay. Now this is nothing but t of t. I mean, power n means t applied n times. Okay. X naught, t power m x naught. Okay. Now we can take, so let's assume n is greater than m. Okay. N is greater than m. So you can take c power n outside. Each time you take out the c power n outside. So d of x naught times t power n minus m x naught. Okay, correct? Hmm? Hmm. Okay. I mean, we are using the property, contraction property, and we are getting this. Okay, we have got this. Now we have to handle this. So that we can do it by like this. This is less than or equal to c power n into d of x naught t of x naught, which is x1, plus t of x d of t x naught. We are using triangle inequality, t square x naught. We go like this, and d of t power m n minus 1, n minus m plus 1 x naught t of n minus m x naught. Okay, that's all. Huh? M greater than or equal to m, c power n I have taken. So c power m, n greater than m, yeah, smaller thing I have to take, and that minus, yeah, correct. So this is m, correct. This is okay. So okay, now you use the inequality again, c power m. Okay, then this is just d of x naught t x naught. But here you can take, there are t you can take, so c times d of t x naught plus up to c of whatever you get, c of that many times, right? N minus m plus 1 d of x naught t x naught. Okay, doesn't matter whatever you get. Okay, we got it something like this. So this is something common times d of x naught t x naught. But this is just 1 plus c plus up to here, which you can take it, which c is positive, so you can take it up to infinity. C is less than 1, so this is 1 minus c. Geometric series. Hope all of you know this. Okay, 1 minus. So this is just a number, constant. This is just a number. In fact, it doesn't have n. This is just a number. But of course, I mean, n is greater than m. So this goes to 0 as n and m goes to infinity. Okay. Huh? C less than 1. So yeah, strictly less than 1. We are using that C is strictly less than 1. If it is 1, it will not work. Okay. Okay, so this implies xn is Cauchy, t power n x naught. This is what is xn. I use this xn is Cauchy. So there exists a x such that t power n x naught converges to that x. Okay. Now this is the fixed point. You just have to verify that this is the fixed point. Of course, t power n plus 1 will also go to the same x. Okay. T of x equal to t of t is continuous. So limit t power n x. Okay. T is continuous. So you can take the limit outside. So this is equal to limit, since due to continuity. Okay. Since t since t is continuous. Okay, this is equal to this t of t power n x, which is just t power n plus x, that is also equal to x. Okay, so t of x equal to x. The uniqueness, so t of x, so t of x equal to x. To prove uniqueness, suppose ty equal to y, we have to show y equal to x. Okay, so that is just d of xy equal to d of, so ty equal to this, both are equal to tx ty, which is less than or equal to c times t of xy by the property, contraction property. So d of xy is less than c of t of xy, c is less than 1. Okay, I mean, if they are not 0, then c would be greater than or equal to 1, but c is strictly less than 1. So this implies d of xy equals 0. X equal to y. Okay, that's so we approved contraction theorem. T time? Yeah. Instead of d, I wrote t. Okay. T times d of x. Yeah. Good. Okay. Which is x naught? This is no x naught. We started with x is the limit. X naught. We started with x naught. X like this. Oh yeah. You are right. Sorry. No. We are applying to x. X. Inside the limit. Yeah. Correct. Yeah. Sorry. Yeah. Sorry. Yeah. You are right. Correct. Okay. Now everything is fine. Okay. Well, contraction theorem assumes that. Oh no, I didn't change it. Okay, I have to fix it, and then you can fix it if you want to see the video. Fix this board in one frame and run it, run the audio in the other one, and look at it. Okay, everything will be clear. Okay, that's how we can do. There is no other way, because it was focusing the other board. Okay, yeah, please. You can look at it in case you are watching the video. Okay. Okay. You can keep this frame and then run the other video for audio. But you will not see the mistake. Okay. That's erased. Okay. Okay. So next, I mean, this is possibly corollary or whatever, another proposition, corollary. So, I mean, it need not be the case that T is a contraction. If T power K is contraction for some K, then also this works. Okay. Suppose T power K is a contraction. I mean, the same definition, everything, okay? Contraction. Then also, then T has a fixed point. Okay. Let's assume T power K is a contraction. So T power K has a fixed point. From that, it will follow. Okay. Tk is a contraction. This implies T power K has a fixed point. So T power K x equal to x. This implies there exists x in x, such that. Now we want to prove T also satisfies that. Okay. So to prove that, let us take this dxtx. We want to show this is 0. Okay. This is equal to d of x is T power kx. Okay. Then T of T power kx. Right. I'm just applying Tx equal to x equal to T power k. Okay. Now this is equal to this is equal to that. Okay. Now this is equal to d of tk Tkx, I'm taking it, and T of Tkx. No, Tk of Tx. Yeah. Okay. Now this is less than or equal to c power k, right? D of x Tx. Okay. Now c power k is less than 1. Tx is less than 1. Okay. Since c power k less than 1, strictly less than 1, d of x Tx equals 0. So, same thing. C power k is a contraction. Right? Sorry. Correct. It is just C. Yeah, it's C. Correct. Yeah, this is just C, no CK. Sorry. I'm assuming T power K is a contraction. Then I want to prove T has a fixed point. T power K is a contraction. Then T power K has a fixed point by the earlier theorem, earlier proposition. Then I use this x Tx equal to this, and I apply x is a fixed point for Tkx, so I just apply this. Then I should get C here. That's all. I mean, because of this, Tx is less than C times this, C is less than 1, T is less than 1, so this is, I'm sorry. Yeah, this is fine. Okay. Next proposition, this doesn't use the contraction. So if you have written, if you are ready, I will go to the next proposition. You are ready? Shall I go? Okay. X is compact. Okay. And T from X to Y, or F you can use. When we write T, it's misleading. Usually T is for linear operators. Okay. So, but assume that it's not linear. Okay. T is X, such that D of Tx Ty is strictly less than dxy. Okay. For all xy, for all x not equal to y. X equal to y, it will not. Okay. For all x not equal to y. Okay. Then there exists a fixed point. Then there exists a unique. Here also unique. Okay. Wherever there has a unique is always there. Okay. Unique is clear by the same argument. Unique is clear. Okay. Then there exists a unique fixed point. Proof. Huh? Okay, you know the proof? Tell me. Huh? So of course T is continuous, which we have already verified by this. Exactly. So bounded, it's a infimum. To take the infimum, that will be the thing. Okay. So the map x going to D of x Tx. Yeah, it should be equal to Tx. X Tx is continuous, of course, on from x to real number. Okay. This is y is x. I'm tempted to take it there. Okay. Yeah, x to x, x is compact, T from x to x, and T, not a contraction. This is also a definition of contraction, strict contraction. Okay. Okay. Then there is a unique fixed point. So we consider this function, which is continuous. It is on compact set. So there exists a x naught in x, such that d of x naught Tx naught equal to infimum of this. Okay. Infimum of this d of x Tx. Right? There exists a single x naught such that this happens. Okay. Okay, that's the infimum. So we want to show that this is the fixed point. This x naught is the fixed point. If not, okay, so let y equal to tx naught. We want to show y is itself x naught itself. So then we consider this y ty. Okay, by definition, this should be less than t of x naught tx naught. Yeah. So this is strictly less than that, which is not possible. Since it is the infimum, since this is the infimum, since this is infimum, okay, since this is infimum, please understand what I'm writing. Since this is the infimum, okay, this cannot be less than that. So this should be equal. That means, but that happens that if only if they are equal. Okay. Maybe I don't even write it tx naught. You can write it tx naught t square x naught if you want. Okay. I mean, we have the condition d of tx ty is less than or strictly less than tx d of xy. Okay, here this is x, this is y, this is tx, this is ty. If you use that, so that has to be equal. Okay, so for compactness it's clear, and compactness is important because you take this function from 0 1 to 0 1, you take x going to x by 2. There is a better function in Kumaresan book. You can find some other example. Bit messy. This is easy. So this will not have a fixed point, of course. Okay. In this, compactness is important. Of course, 0 will be a fixed point, which is not there. Okay. So compactness is needed. Okay. Okay. There is one more thing. I have time, and I will not have time to maybe start Baire's theorem in the next class. Let's see. But Baire's theorem is very easy to prove. It's immediate. Okay. So let's see. Proposition. I will take some more time as usual. Okay. So proposition is you consider this thing. Let V be contained in B of x, some closed normed linear space. NLS, normed linear space. We have a V which is B of x, something. You can take B of x itself or some subspace. X is any set. Any set. Collection of functions on B of x with respect to supremum norm. That's a Banach space. So I take a V which is contained in that. Now T is from V to D. Need not be linear. Okay. When I write it, it may look like linear. Need not be linear. I mean, usually within vector space, we will consider only linear function. Okay. Thank you. But this need not be linear. Yeah, closed norm linear space. That's what I have written. Okay. T from V to V need not be linear. Satisfies the following. Satisfies the following. T of F. These are all functions from S to R. Okay, I take it from R. Real line, not complex line. Okay, so that I can write the inequality. T of F is less than T of G if F is less than or equal to G. If you have a function for each F is less than equal to G, means F of T is less than G of T for all T. That's what F of F is less than or equal to G. Then the function T of F is less than T of G, which is this property is what is called monotone. T is monotone. That's what it means. That's the property I've written. T is monotone, number 1. 2, T is not linear. It satisfies the following. F plus C. C is a constant. Constant times 1, which is, how do you prefer? C means it's a constant function. It's a constant function. If you have a constant function, T plus C, okay, constant function, is less than or equal to TF plus some beta C. There exists a beta. Okay, such that beta times C. That's all. I have a map. V is a subspace of bounded functions on S. Okay. V is a subspace. I have a function from V to V, which is monotone. It takes f is less than g, Tf is less than g, and it satisfies this property T of f plus c, where c is a constant function, then Tf plus beta c, where beta is some constant between 0 and 1, like the earlier contraction one. Okay. This is for all f in V, for all c in R. Okay. Bs is all bounded functions from S to R, bounded functions. Pointwise. F of t less than or equal to g of t for all t. That's what it means usually. This is V is a closed nonlinear space. There is nothing up to here, there is only V, nothing else. Okay? V is closed nonlinear. V subset of this is a closed nonlinear space. We need completeness, right? So that's why we are taking. We want to use the same fixed point theorem to prove this. Okay? We will only prove that, see, then T has a, I haven't written that, then T has a fixed point, unique fixed point. Okay. I mean, we have all this condition. Using this condition, we will only prove T is a contraction with the constant beta. That's all. Where are we getting completeness? Closed means completeness. B of S is complete. Something closed is complete. V is complete. So we only need to prove, I mean, it's enough to prove, maybe enough to prove, T is a contraction with the constant beta. Okay. The contraction comes with a constant, and that constant is beta. Okay. Okay. So what do you have to prove? Let's see what you have to prove. We have to prove, I mean, whatever the metric is, there is a metric in V, which is given by that infinity norm, which is given by the norm. So we have to prove that whatever the D infinity is, I will erase it. I will just reminding you, I will erase it. D infinity of 2 f and g is less than or equal to beta times d of I. Here there is a D infinity of T f Tg is less than or equal to d of fg. But this is equal to norm f minus g infinity, beta times f minus infinity. This is just Tf minus Tg infinity. Okay, we just have to prove this, right? So we have to prove this. To prove that, we have to prove this. So we have some beta times c, some condition. That condition c, we take it to be f minus g. Okay. So I will erase this. Let fc equal to f minus infinity. Okay. I'll come back to this. Okay. C equal to f minus g infinity. Okay. Then this implies f minus g infinity means what? F of x minus g of x mod of this is less than or equal to c. That's what it means, right? By for all x. That's what it means. So this is equivalent to saying f of x is, I mean, c equal to this means less than or equal to g of x plus c. And g of x is less than or equal to f of x plus c. Eh? For all x. Okay. Or I remove this f x. Or I remove this f. This implies T of f, okay, is less than or equal to, by the condition, T of g plus c, okay, which is less than or equal to Tg plus beta c, okay, for all x or whatever. If you wish, you put a x here. I mean, that's what it means. Okay. for all x. For all x in, sorry, yes, not V, for all x in S. Okay. Okay. So this implies TF minus TG, okay, is less than or equal to at x is less than or equal to beta times C is that F minus G infinity for all x. So this and similarly TG minus similarly TG minus TF is less than or equal to beta times norm F minus G infinity. That's all for all x. Okay. So this is what we want. So these two implies T of F minus T of G infinity is less than, thank you, is less than or equal to beta times norm F minus G infinity. That's all. This is what you exactly. It's true for all x, so we can do that. That's the definition of this. I mean, this is that no. By this we mean for all x, this is true. That's the definition. Okay. This is because it's true for all x. This is true. Okay. And this is exactly what it means. D of TF Tg less than or equal to beta times D of. So it has a fixed point. Okay. So this implies T has fixed point. Okay. More about fixed point, you will see either in assignment or exam. Okay. Sorry. Okay. So I have some more time. I'll prove Baire's theorem. Okay. This is okay. You have copied. Shall I start? Yeah. I will just write theorem. Baire. Okay. No. Before that, I will make a definition. I'm sorry. I have to make a definition. So X is a metric space. Okay. X is a metric space. F contained in X is said to be nowhere dense. Or S contained in this. F usually F is for closed set. Okay. If interior, we have defined interior, okay, of S closure is empty. Okay. For example, rationals does not have any interior. Both irrational, rational does not have any interior, but the closure is everything. But they are not called as nowhere dense subset. Okay. Nowhere dense subset we can usually define it and consider for closed set. So here, if you have any set, then you can consider the closure. Closure has no interior. Okay, that's how we should do. Subset of this space, yes. Subset of yes. That nowhere dense you are asking? It will be nowhere dense. I mean, the open sets are considered inside X. The open sets are, it's supposed to be open in X. If you say open in X, that will be always contained in that. So, I mean, that way S is open all the time. This is the whole set, right? It will be open. There is nothing. I mean, the interior you are taking in X, not with respect to relative topology or metric. Okay. So whenever we have something, countable union of that is also something small for us in math. For example, rational numbers, even though it's dense in R, they are very small when compared to, in cardinality, they are very small when compared to irrational numbers. Okay. because you can just count it. You can count it means what? It will take infinite time, but still you can enumerate it. Okay, in a sense you can count it. Okay, but uncountable, there is nothing. There is no way you can enumerate it. Irrational numbers are too many. You don't know all of them. In a sense, you know all rational numbers. In a sense, you know all rational numbers, but you don't know all irrational numbers in any sense. I mean, you can write it as a sequence or something, but there is no way you can account it for. Okay, you don't have an enumeration of that. Okay, so in that way, irrational numbers are larger. I mean, the cardinality of irrational number is much more than rational numbers. Though they are both infinite, there are different infinity. Okay, this is countably infinite. That's not. So if you take set, metric space or something, there are some sets which are smaller, even though they are all infinite, uncountably infinite. You say something is smaller. For example, we will see that if you take the collection of functions on C01, okay, then the differentiable functions are, differentiable functions are very small. Okay, in fact, a function differentiable at one single point, any point, is also very small. The functions which are nowhere differentiable, they are not differentiable anywhere, they are much more than whatever the differentiable functions are in the continuous function. Okay, that's what we will prove. So that's so we want to quantify that smallness. Okay, that is through this nowhere dense. Okay, that is what is called meager. Meager is something small. This is another definition. Yeah, well, let's use only closed set. Okay, for f contained in X is closed. Okay, is said to be meager or first category. Is the spelling right? I'm not sure. Is spelling right? Or okay, first category. It's called first category. Huh? Do you know what is the spelling? Sorry, okay. Meager. These days when I type, it automatically. Okay, I will use this. Okay, this is first category or first category is also called first category. Okay, if f is equal to union of fn, countably many fn, with each fn nowhere dense. Okay, any set which can be written as countable union of nowhere dense subsets is called a meager set or first category. Okay, a set A contained in F or whatever, yeah, F contained in X is said to be second category. This has something to do with category theory. Second category, if it is not first category. Okay. If it is not first category, it's called second category. Okay. It cannot be written as countable union of nowhere dense subset. Yeah, we define it for closed set. Otherwise, you have to take the closure and other things. Okay, why do that? Okay. Any closed set of what? Second category. That's the definition. For example, rational numbers can be written as countable union of singletons or nowhere dense. You can write rational numbers as countable union. That's not something of second category. Okay? That's dense in R. Where Fn is also closed. Okay, Fn is closed. I'm sorry. Eh? That's what I'm saying. That's why I use closed. Rational can be written as union of nowhere dense subset, but that is not something of consideration here. So, I mean, this F1 also with F1 closed nowhere dense. Okay, F1 closed nowhere dense. I mean, we can even forget about the definition. You can consider nowhere dense for closed set. Okay, we can consider for only closed set. Okay? If the interior is empty, it's called nowhere dense. We consider only for closed set the definition. We don't need to take closure. Okay. This is Baire's theorem. Baire category theorem.
But then he's going to say there existed
If you take any open ball,
it's
it should intersect with the complement.
it has a its complement is there.
Complement with the open and dense. If you take any open ball, it should intersect with the complement. Complement is dense means rational complement is for closed set you are saying. Yeah, that's right. For closed set, correct. Yeah. Yeah, for closed set, the complement is dense. Correct.
It will be open.
Yeah, open and dense. Baire's theorem. This says that X is complete. Okay. And UN contained in X is open and dense for all N. Okay. Okay. Then the intersection UN is dense. It need not be open, but it is dense in X. Okay. You take countable collection of open and dense subsets, its intersection is also open. So its intersection is also dense. Okay, dense in X. Okay. What do you have to prove? To prove that this is dense, these are all open and dense. Okay. This is to prove this is dense, something is dense, we have to take any open ball anywhere in X that should intersect with this. That's what dense means. Okay. Dense is equivalent to taking any ball which intersect with this. So it, say it again. That's one way. That means precisely that we have remarked earlier. Okay. If you take any open ball, that should intersect with intersection this set. Okay, you call it U if you want. Then U equal to this. Okay, need to prove, or enough to prove, any open ball intersects with this. Any open ball will contain a closed ball of half of that radius. So it will be enough to prove any closed ball intersects. Okay, enough to prove any closed ball. Okay, let's call this B naught. Any closed ball. B naught intersection this is intersection n equal to 1 to infinity un is not equal to empty. Okay, it's enough to prove any closed ball. I call it closed ball B0. I'm not taking closure or something. It's a closed ball. All the balls we are going to consider now iteratively are closed balls. Okay, I will write it. It's enough to prove any open ball. Any closed ball intersects is also fine. If the closed ball intersects, half of the radius, open ball with half of the radius will be open ball, that will intersect, right? So it's enough. Sorry, twice the radius, whatever. Any open ball, it's true for, I mean, if you prove for any closed ball, then it is true for any open ball. Okay. Okay, how do we do that? Okay, now we want to B intersects with that we want to say. First B naught, since U1 is open and dense, okay, U1 is dense, B naught intersection U1 is not empty, correct? Okay, but this is open. I mean, take the interior of this. Interior of, but then interior of B naught if you want. Intersection U1 is open. Okay. So there exists a ball. Let's assume, I want to take this B naught as with radius delta. Okay. For any closed ball, let B naught with radius, some radius. It has some radius. You call it delta, R or delta, whatever, epsilon, whatever you like. Okay. B naught is with radius delta. So B naught intersection U1 is here, this should contain, this is open, another ball. So there exists a, I mean, which is contained here, which is contained here. There exists a B1. Okay, I'm only saying that it intersects B1 with radius delta by 2 less than delta by 2. Yeah, such that B1 is contained in B0, both are open, P0 intersection U1. Exactly, you go on like this. From UN to you go to UN plus 1. So there exists, so choose Bn ball with closed ball. This is closed ball, okay? B1 is closed ball. There exists B1 closed ball. Okay, you go on doing this, Bn closed ball, but with smaller radius, ball with radius delta by 2 to the power n, such that Bn intersection, sorry, Bn intersection, yeah, Bn is contained in that. I mean, that's what Bn is contained in that. Yeah, contained in that. Yeah. Yeah, so less than delta by 2. Yeah, that's what it is. Less than delta by 2. Yeah, but it will be a strictly positive number. Okay? So it's less than delta by 2. Bn with less than delta by 2 power n. Okay, you take a smaller one, less than delta by 2 power n. Bn is contained in Bn minus 1 intersection Un. Okay. Okay. So this Bn closed to set decreasing, that is Bn contains Bn plus 1 exactly, and diameter, which is twice the radius, diameter of Bn goes to 0. Okay. So our man Cantor says that, Cantor says intersection of Bn equal to some singleton x. Okay. And that x is going to be in the intersection of all Un and Bn's also. And x is in original B0 also. It's x is in all Bn's also. So it's going to be B0 also. So this basically says that B0 intersection, this intersection of n equal to 1 to infinity Un is not equal to empty. That's what we wanted to prove. Okay. Why did I define category? I will come to that. So that is your question, right? Corollary. Corollary. X is complete, then X is of second category. Proof. If X is equal to union of Fn closed, okay, and Fn nowhere dense, okay, nowhere dense, then Fn complement is open and dense. Okay. This implies intersection Fn complement, okay, is dense in X. Okay, right? So this implies union of n equal to 1 to infinity Fn whole complement. This is dense. Okay, this complement is dense. In particular, this is, I mean, is more than that, more than being second category. Okay. In particular, I mean, I don't want to, this is a contradiction, but I don't want to do that. I just take some Fn. Start with this. Start with any Fn closed and Fn nowhere dense. Then these things are true. Okay. In particular, union of Fn n equal to 1 to infinity is not equal to x. Okay. I mean, if I assume, then I have to say contradiction or something. Okay. I start with Fn, which are closed and nowhere dense. Then Fn complement is open and dense. So intersection has to be dense. In particular, intersection has something. Okay. Then this union cannot be equal to that. That's all. This is second category. So this has many applications. We will see at least 2-3 of them. Okay. I will stop with this. So we'll start the applications from the next class.